Imagine a world where tiny particles called atoms are constantly seeking balance. This quest for stability often leads them to form ions, which are charged versions of themselves. Let's embark on an adventure to understand how and why these ions form, especially focusing on the most eager participants. The elements in groups 1 and 2 and groups 6 and 7 of the periodic table. Before we dive into the periodic table, let's clarify what ions are. Atoms are made up of 3 types of particles: protons, neutrons, and electrons. Protons have a positive charge, electrons have a negative charge, and neutrons are neutral. In a neutral atom, the number of protons equals the number of electrons, balancing out the charges. However, atoms are not always content with their electron count. To achieve a more stable lower energy state, they may gain or lose electrons, turning into ions. When an atom loses 1 or more electrons, it becomes a positively charged ion, or cation. Conversely, when an atom gains electrons, it becomes a negatively charged ion, or anion. Now, let's meet our first group of enthusiastic ion formers. The elements in groups 1 and 2 of the periodic table, known as the alkali metals and alkaline earth metals, respectively. Group 1. Alkali metals. Elements lithium, Li, sodium, Na. Potassium, K. Rubidium, Rb. Cesium, Cs. Francium, Fr. Behavior. These elements have just 1 electron in their outermost shell. This single electron is like an extra luggage piece that they can't wait to get rid of. By losing this electron, they achieve the stable electron configuration of the noble gases, the elements in group 18, which have full outer shells. Result: when they lose their 1 outer electron, alkali metals form cations with a charge of ℧1. For example, sodium, Na, loses 1 electron to become Na+. Group 2. Alkaline earth metals. Elements: beryllium, Be, magnesium, Mg, calcium, Ca, strontium, Cor, barium, Ba, radium, Ra. Behavior. These elements have 2 electrons in their outer shell. They are keen to lose both electrons to achieve a stable configuration. Result: when they lose these 2 electrons, they form cations with a charge of +2. For example, magnesium, Mg, loses 2 electrons to become Mg2+. On the opposite side of the periodic table, we have groups 6 and 7, known for their hunger to gain electrons and form anions. Group 6, the oxygen family, chalcogens. Elements: oxygen, O, sulfur, S, selenium, Se, tellurium, Te, polonium, Po. Behavior: these elements have 6 electrons in their outer shell. They need 2 more electrons to fill their shell and reach the stable configuration of the noble gases. Result: by gaining 2 electrons, they form anions with a charge of 2. For example, oxygen, O, gains 2 electrons to become O2. Group 7, halogens. Elements: fluorine, F, chlorine, Cl, bromine, Br, iodine, I, astatine, At. Behavior: these elements have 7 electrons in their outer shell, just 1 short of a full shell. They are highly reactive and readily gain 1 electron. Result: by gaining 1 electron, they form anions with a charge of 1. For example, chlorine, Cl, gains 1 electron to become Cl. The driving force behind the formation of ions is the pursuit of stability. Atoms are most stable when they have full outer electron shells, like the noble gases. Elements in groups 1 and 2 find it easier to achieve stability by losing electrons, becoming positively charged ions. Meanwhile, elements in groups 6 and 7 prefer to gain electrons, becoming negatively charged ions. Table salt, NaCl, sodium, Na, from group 1, loses 1 electron to form Na+. Chlorine Cl from group 7 gains that electron to form Cl. Together, They form ionic bonds to create table salt. Magnesium oxide, MgO. Magnesium, Mg, from group 2 loses 2 electrons to form Mg2+. Oxygen, O, from group 6 gains those 2 electrons to form O2. They combine to form the compound magnesium oxide. The formation of ions is a fascinating dance of give and take, with atoms striving to achieve the harmony of a full outer shell. Groups 1 and 2 are eager to lose electrons and become positively charged, while groups 6 and 7 are just as keen to gain electrons and become negatively charged. This interplay is fundamental to the chemistry that shapes our world, from the salt on our tables to the materials in our technology.